another problem from the blind 75 list, and today we're going to solve another linked list problem in which we're going to reorder the list. Previously, we went over two other linked list problems which are pretty simple to understand and work with. Now we need to work with a slightly more tricky linked list problem. So let's go over here and use a color to set up one linked list. So we have a linked list, let's say with 1, 2, 3, 4, and 5. A little bit messy, but I think you get the gist of it. What we mean by reorder is that basically in this particular problem, so first we need to break down what reordering means. First we need to to reorder the list, we need to basically pretty much create, and I'm not saying we need to create another list, but presume that this list is being reordered in the next one. So that is what we're going to do. So first one is brought over to the new list, right? Whatever that maybe, I'm not probably arrows, because that's our that's what's showing what the linked list is. So one is brought over and into the new list, right? But the next thing is we bring on 5 as the next element, the linked list, right? As the second element. So the reordered linked list has 5 as the second element, right? Similarly, then we bring in 2 into this new reordered list. 2, the 2 is brought over. Similarly, now 4 is brought over. Again, I can do it a little more cleanly. And at the end, simply 3 is brought over, right? So I think you're getting the gist of what reordering means in this particular question. We need to alternatively bring an element from here once, then 5 from 1 from the end, then from the start, then from the end, then from the start, right? So alternatively from start to end, start to end, start to end until we complete the list, right? So that is how we are reordering a list in this particular problem. But we understand that, right? But how do we solve this problem, given that we have a solution that pretty much shows O n time complexity, basically. Do that. Let's understand this again. So let's write our linked list again. So there's 1, there's 2, there's 3, there's 4, and there's 5. Given that these are the numbers that we have, right? These are the numbers we have in a linked list. We need to now basically reorder this linked list as we discussed previously. How do we go about doing that? So imagine, presumably, in this case here, is that at a certain point in time, so at a certain point, we need to find the midpoint of this particular problem. That is the first thing we need to do. And why do we need to do that first? The reason for that is basically, if we have the end of the linked list, quite simply, if you want to reach time of ON, instead of rewriting that particular list, the simple thing we can do there is just reverse this linked list, cut this connection off, and just reverse this connection from 5 to 4. Basically, then we have one section, right? We have the midpoint, right? Now that we have that, then we can simply write 1, and then basically enter this number and pretty much move alternatively between them, basically. How do we find the midpoint? That's the first question, right? To find the midpoint, we use the 2 pointer or a slow and fast pointer technique rather, right? That is how we find the middle of a linked list, right? We're using a slow and fast pointer technique. In this technique, basically, to find the middle of the list in one pass, we use the slow pointer to move one step while the fast pointer moves two steps. When the fast pointer reaches the end, the slow pointer will be at the middle of the list. So what do you mean by that? So we have a slow pointer here at 1, right? And we have a fast pointer here. Not even at 1. Slow pointer at 0 and a fast pointer at 0, right? No values associated. When the slow pointer moves to 1 step, the fast pointer moves to 2, right? Then the slow pointer moves to 2 in 1 step. The fast pointer moves to 4, right? Then the slow pointer moves to 3, and the fast pointer moves to 6. There is no 6 here, so the fast pointer is pointing to null value. What does this mean? This means that we should have reached the midpoint of our problem, and that is how the slow and fast pointer techniques work in this particular problem, right? So now that we have the midpoint, what do we need next? Second thing is to reverse the second half of the list. So once the middle is found, we reverse the second half of the linked list, and we need to arrange the second half in reverse order to interleave it with the first half. So we've already covered how to reverse that, why reversing is important. So we just show that graphically here and move forward. So we just reverse the order of 5 and 4, right? Now that we have done that, the third thing is to merge the two halves. We interleave the nodes from the first half and the reversed half second, and we alternate nodes from both halves and update the links accordingly. So linking is an issue with linked list, right? That's why we needed to reverse this. Otherwise, we could have directly done as we showed before, but we have reversed the linking, so the relationship of the reverse linking remains the same. So given that now what we do is just bring in 1, link it with 5. This is interleaving, right? This is what we mean by interleaving a list in this problem. It's refers interleaving over and over again. So this is what interleaving is, right? So then we bring on 4 and then we bring on 3. That is basically our list reorder. Now that we get the gist of this particular problem, how do we move forward in solving this problem? So let's just code this out now that we understand what we need to do logically. So basically, if we don't have a head or we don't have any value in head.next, we need to return basically. Why? Because there's nothing there, so we need to just return an empty value basically. So let's set that up. Then we need to go to the first step where we need to find the middle value using the slow and fast pointer technique. So we basically set up the slow and fast pointers first. Next, in this process, once we have initialized the slow and fast pointers, we need to now uh, check our checking mechanism is as long as there's a value in fast or fast.next. As long as there's a value in these two variables, we keep running this loop and just moving slow pointer ahead. But the moment fast or and fast on next have a null value attached to it, we need to stop because that slow the point where slow pointer is right now is the middle value of the value. So we set up a while loop to sort that problem out. With that out of the way, we now need to code the second step where we reverse the second half of the list. A simple reversing a while loop that we discussed in the reversing linked list problem. We just need to use that here to solve this problem. I'm not explaining this code here because we've already covered this code in a simpler linked list problem. If you're a little bit confused about that, please refer back to that because the main gist of this particular problem is the reordering mechanism. Reversing is a completely separate problem. So please review that if you don't understand that and move to this video next. All right. Now that we have the reversing sorted out, the next thing we need to do is to merge the two halves together and interleave them. So that's step 3. So to interleave them, we need to first declare the first and second pointers and equate them to the head previous pointer as well. So the code that you see here is basically first while as long as second dot next has a value, the temp1 and temp2 values store the first next and first second values, and then the first next and second next values are changed to second and temp1 for the time being. Next line of code, we change the values of first and second as well. So we change second to temp. So with that, we are able to pretty much solve this problem. The time complexity as discussed one is O of n, and the space complexity is O of 1 since we're only using constant extra space for pointers and we modify the list where it is. So with that, let's run this code and see if it works properly. Solves both cases here. And if we run the submission case test as well, it has been accepted and the problem is working fine. So with that, we're going to wrap up this problem and we'll see you in our next video. Thank you.